Hi everybody, this is Miss McClellan here to go over notes IM2 8.3.1 with you. How does the area change? Now, part of this course so far has worked to investigate how to enlarge or reduce a shape to create a similar figure. We've also studied how to use proportional relationships to calculate the lengths of sides of similar figures. So for example, let's say I gave you this trapezoid. And it has a length up here, 3. And I told you that it was the original trapezoid. If I told you there was another trapezoid which was similar, and it had length, I don't know, how about 15? And this is the image. And I wanted to know, what is K, the scale factor? Well, the scale factor is always image over original. So it would have been 5, because 3 times 5 is 15, and 15 divided by 3 is 5. We're going to be building off of our knowledge of scale factors today. So let me just erase that. So let's write in our learning goals. We have a couple. Our learning goals, our first one is that I will be able to use linear scale factors. And number 2, this is a goal we've already done. Number 1 was one we've already done. Number 2 is that I will be able to find an area scale factor given its corresponding linear scale factor. Period. Okay, let's keep going with the first problem. This problem is called Mighty Mascot. To celebrate our victory, let me clear all of that. To celebrate the victory of our school's championship girls ice hockey team, the student body decides to hang a giant flag with our school's mascot on the gym wall. This is the flag. To help design the flag, our friend Archie created a scale version of the flag measuring 1 foot wide and 1.5 feet tall. So let's see. Oopsie. So we have that Archie's version is 1 foot tall and 1 foot wide and 1.5 feet tall. And the student body thinks that the final flag should be 3 feet tall. So that means this length will be 3 feet. How do we know what this length is going to be? Well, the scale factor is going to be the image. This is the image divided by the original. So 3 over 1.5, which is 2. So I can solve for this missing length here by doing 1 times 2 is 2. This missing length x is 2. That's how wide the enlarged flag should be. Let's keep going. If Archie uses $2 worth of materials to create his scale model, how much will the materials cost for the full-size flag? So this little flag is $2. And the question is, how much does the big flag cost? Well, the most common answer, and just a heads up everybody, this is not the correct answer, but the most common answer is that if the length is being multiplied by 2, then maybe the area is multiplied by 2. Is that right? Well, it's not, but that's the most common error. Most common answer. So let's type that in. If the length is multiplied by 2, then maybe the area is multiplied by 2. And we're going to investigate and see how come that doesn't quite work. All right, so part C says to obtain a resource page. And I've got a copy of it ready to go on Desmos. We're going to look at Archie's flag. And let's go to Desmos right now. And we're going to see, hey, let's check how many little flags fit in the big flag. So I'm going to take these little flags and I'm going to move them to the big flag. Okay, let's see. Oopsie. I won't use that one. Yarg. They're too small. Okay, I'm going to try again. Take this little flag and move it to the big one. Sorry, students. How many are going to fit? I wonder. Got one in there. 2, 3, 4. Okay. It looks like 4 little flags fit inside. 4 of Archie's flags fit inside the big one. What does that change? So, let's see. It turned out that 4 of Archie's little $2 flags fit inside the big one. So in part B, we said that it would cost $2, but we were wrong. Sorry, we said $4. $4, but we were wrong because each of Archie's flags cost $2, and instead of doubling the number of little flags, we have to multiply that by 4. So actually, the big flag should cost $8. All right, next problem. The student body is reconsidering the size of the flag. It's now considering enlarging the flag so that it is 3 or 4 times the width of Archie's model. Estimate how many small flags would fit into each large flag. Dude, I don't know. Maybe in the 3, maybe we can fit 6. In the 4, maybe we can fit 12. No, maybe I should multiply by 4. So maybe in the 3, we can fit 12. And in the 4, we can fit 16. Let's find out in just a minute. We still have to check our estimate. So based on our estimate, how much would the materials be for the similar flag? That is 3 times the width of Archie's model. Well, that similar flag, which is 3 times. Each of Archie's is $2. So I'm going to do 2 times the number of flags that I think are going to fit in times 12. And that's 24. The reason I got 12 is because I'm thinking maybe you always multiply by 4, but we're going to check that. Okay, based on our estimation, how much would the materials for a similar flag be? So this is again based on our estimate. Each of Archie's flag is $2. I'm guessing there are 16 in there, so 2 times 16, and that's 32. Let's see if that's right. Okay. So now it says obtain a copy of 8.3.1 resource page, and we're going to figure out by counting how many fit in. I might ditch Desmos because I feel like this is not that easy to see, but let's see. Okay, I think I can do it. So how many of these little flags are going to fit into this big one? Let's see. I want it to be 2, 3, 4 times the length. So 4 of the lengths. Okay. How many fit? 2, 3. Dun-dun-dun. How's your day, everybody? You're watching the video. That means you missed class. Hope you're feeling well. Dun, 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 dun. We missed you in class. Oopsie. Didn't mean to do that. Okay. I did it again. I'm going to mess it up a little bit. Oh well. Almost done. Taking a while. It's a nice day out. Do, do, do. Do, do, do. All right. I'm not going to turn those upside down. We can count how many flags we need with this. Let's see. Maybe I will. I don't know how to turn it upside down. Okay, anyway. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So when I took this flag and I enlarged its length by 4, so here length is times 4. The area did not increase by 4. The area is times 16. I know because I can fit 16 of them in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Huh. That's interesting. Let's check for a 3 by 3. If I make the length, for a 3 by 3, I've basically already done it. Just take this part off. So if I triple the length, this is times 3 for length. What happens to the area? 1, 2, 3, 4, 5, 6, 7, 8, 9. Area times 9. Huh. What do you notice? Okay, I'll go back here. So we just checked, and we got that for the flag that is 3 times the length, 9 little flags fit in. And let's see. For the flag that is 4 times the length, 16 little flags fit in. So how much does that mean the materials would cost? Well, Archie's flag was $2, so I'm going to do, for the similar flag that's 3 times the size, it'll be the price of Archie's flag, 2, times the number of Archie's flags we needed, 9. So 2 times 9, that's $18. And how much would the materials cost for the 4 one? Well, Archie's costs 2. 2 of Archie's flags fit in. There are 16. Archie's flag costs 2. 16 little flags fit in the one that was 4 times as wide. So 2 times 16, and that's $32. Now, if we look, our estimates, somehow we got this one right because we multiplied by 4. And this one we didn't get right. We thought it might be 12. So there's a pattern to be found here. We should write down any observations we have. Oh, would you know it? There's a Desmos screen for that. Next. Let's clear this. Okay. So for when Archie's flag, well, when we were considering one that was two times Archie's flag, the number of triangles that fit in was 4. And the cost of that flag was $8 because Archie's flag cost 2. We multiply the numbers that fit. Okay, when the length of the side increased by 3, the number of triangles that fit was 9, and that cost $18. And when the linear scale increased to 4, the number of triangles that fit were 16. Made that cost $32. I noticed that the one thing I notice is that the linear scale factor is the square root of the area scale factor. I'm calling this the area scale factor because I started with an area of 1 and I multiplied that by 16. So I'm noticing that the scale factor, the area scale factor is the linear scale factor squared. For example, if the length increases by a scale factor of a equals 4, then the area increases by a scale factor of k squared equals 16. All right, I'm going to put this into our notes. Copy, paste. All right, next problem. So now we're going to use our observations from problem 584 to answer the following questions. So here we go. Kelly's shape at right has an area of 17 millimeters square. If she enlarges the shape with a linear scale factor of 5, what will the area of the enlargement be? Well, I noticed that the area scale factor is the linear scale factor squared. So if the linear scale factor is 5, then the area will enlarge by 25. Because that's 5 squared. So I'm going to multiply 17 by 25. Oof. How much is that? Let's see. 16 quarters would be 16 quarters would be $4. So I think this is 425 millimeters squared. Okay, cool. Next problem. Examine these two similar shapes. Now this particular problem is on your test. What is the linear scale factor? Well, I'm going to say, I'm multiplying by 4. This is a little bit ambiguous though, because it doesn't tell you which is the image and which is the original, so you sort of have to make a choice. If you wanted, you could call this 1/4. It would just mean you were considering your original to be the bigger one. So linear scale factor, based on the choice I just made, is 4. The area scale factor is 16, because that's 4 squared. Now, what is the area of the smaller figure? Well, to get from the small figure to the big figure, I would multiply by 16. To go in the other direction, I would divide by 16. So I'm going to do 656 divided by 16, and that is 41 units squared, period. That's the answer. Okay. While ordering, what's this? Sorry. Anyway, while ordering carpet for his rectangular office, Trin was told by the salesperson that a 16 by 24 foot piece of carpet cost $800. Then Trin realized that he read his measurements wrong at the office, and he actually needed 8 by 12. And the salesperson goes, "Hey, no problem. That'll cost $400. Is that fair?" Well, let's decide what that price should have been, because we have to think about it. So if I start with 16 by 24 and I end with 8 by 12 for length, then the linear scale factor, K, is 0.5, because I'm reducing by half. Now the area scale factor, and we consider area to be price, should not reduce just by half, but it should reduce by half squared. So the area should go down by 0.5 squared, which is actually 0.25, which is a fourth. The new price should have been $200. So the $400 quote was incorrect and unfair, because area is the linear scale factor squared. And that's actually the last problem, everybody.